in this problem, we want to find I0 of t for t greater than 0 using the step-by-step method. We're going to utilize a problem-solving strategy entitled Using the Step-by-Step Approach. Here's our circuit. We have a single inductor over on the left. We have a switch that opens at t equals 0. The first step in our problem-solving strategy is to realize that I0 of t is of the form k1 plus k2 e to the minus t over tau. The next step of our solution, we're going to draw the circuit at t equals 0, because what we're doing is we're working toward identifying values for k1, k2, and tau. So here's our circuit at t equals 0 minus. Notice that we've taken the inductor and we assume steady state in the circuit, so we replace the inductor with a short circuit. And if we look at this circuit, we need to find IL of 0 minus. If we used mesh analysis, we have 3 meshes. Let's look at using nodal. So I'll pick that as a reference, and I'm going to define 2 node voltages, V1 and V2. And now let's apply Kirchhoff's current law to those nodes. So for the node on the left, we'll have V1 over 4. That's the current leaving in this direction. Then we'll have V1 minus 12 over 6. That's the current flowing down. And then V1 minus V2 over 3. That's the current flowing left to right. That's equal to 0. And we can simplify this equation to 3/4 V1 minus 1/3 V2 equal to 2. So here's one of our 2 equations that we'll need now. Let's do KCL at this node. We'll have V2 minus V1 over 3 plus V2 over 3 equal to 3. So now we have minus 1/3 V1 plus 2/3 V2 is equal to 3. Now, we solve. We get V1 equals 6 volts, V2 equals 7.5. And if we look at our circuit, we can see that IL of 0 minus then is 6 over 4, or 1.5 amps. And if we really wanted to, we could say, well, we can also solve for I0 minus, and that would be 7.5 over 3, or 2.5 amps. We really don't need that. We'll use it later on if we decide to plot it. But now we've solved for the initial condition on our inductor. We know, for instance, that the inductor current is continuous through the switching operation. So now we're going to draw the circuit at t equals 0 plus, which is the next step in our problem-solving strategy. We replace the inductor with a current source equal to IL of 0 minus. So there's our inductor. Now if we look and apply Kirchhoff's current law at this node, we can see there's 3 entering and 1.5 leaving, so this current has to be 1.5 amps. So then I0 of 0 plus is 1.5 amps. So that completes our analysis at t equals 0 plus. The next step is go to t equal infinity. Draw the circuit. Again, we're going to assume that we're now in steady state. So the inductor again is replaced by a short. And now we can calculate I0 of infinity simply by current division. We'd have 3 times, we want the current here, so we're going to have 7 over 7 plus 3. So I0 of infinity is 2.1 amps. Now, step 5 says find the time constant. And for an RL circuit, remember our time constant is L over R Thevenin. We want to find the Thevenin resistance seen by the inductor. Now remember, the inductor is at this part of the circuit. So let's draw the circuit for calculating tau. Here it is. The current source we turned to 0 and replaced it by an open. We made a port or an entry point where the inductor was. We want to find R Thevenin looking in there, and if we look at the circuit, we can see that R Thevenin is 10 ohms. So our time constant is L over R Thevenin. So we have 100 millihenries divided by 10 ohms, which is 10 milliseconds, which is 0.01 seconds. Now, we've evaluated all our constants. Now that we know what the solution is, we can go in and plug in values. So I0 of t then is 2.1 plus 1.5 minus 2.1 e to the minus t over 0.01 amps. So then I0 of t is 2.1 minus 0.6 e to the minus t divided by 0.01 amps. And since we have the solution, let's plot it. So we calculated that before the switch closed, the current was, before the switch moved, in other words it opened, the current's at 2.5, then it jumps down to 1.5, and its final value is 2.1, so it does something like this.